All right, counting and probability problems. These are from the 2008 exam. Look at some practice on this. Number 12. If you're dealt 3 cards from a shuffled deck of 52 cards, what is the probability that all 3 are face cards? Well, so we've got to answer our 2 basic questions. Is it with or without replacement? Well, they don't say it absolutely explicitly, but in a card dealing problems, almost always it's without replacement. So you're going to have 3 cards in your hand. They can't be the same card. So it's without replacement. And we're not told that we care about order. The question doesn't involve order. And it's without replacement, and therefore we don't have to include order. Remember that a subtle thing is that even if what you care about doesn't include order, but replacement happens, like die rolling problems are a big example of that, you actually should do it with order. But here, order is totally immaterial, and we're doing it without replacement. And so it's going to be choose. And so what is the 2 things? We want the sample space. So that's going to be the denominator. That's all the ways anything can happen. And that's going to be 52 choose 5. Let me bring up the math toolbar here. I forgot to. Hello. Where is it all? There we go. Yeah, there we go. So that's going to be no line. Sorry, I forgot to put it up on this version of Workplace. Okay, that's 52 choose 5. I'll just copy that, it's easier. And, choose 3. Sorry, I'm so used to dealing with 5-card poker hands. 52 choose 3 on the bottom. Well, what are we looking at? The things we actually care about, the event we actually care about is that we get it from the face cards. Well, there's 4 suits, and there's Jack, Queen, King. There's 3 values for each. There's 12 face cards, and we're choosing 3 out of those. So there's 3 ways to choose from the 12 face cards, or there's 12 choose 3 ways, rather. And there's 52 choose 3 ways of getting at anything. One of the things that I find useful is that there's a slight change in perspective. You're looking at the 52 cards, and you don't know if you're going to get face cards, but you're interested in the probability of it. The way you can think about that, the numerator here, is imagine that the face cards are all there is. That gives you the numerator. Pretend there aren't anything but face cards. How many ways, if somebody actually purposely gave you the face cards, how many ways could they do that? That's going to be the numerator of this probability problem. And let's go ahead and just evaluate that. 11 over 105, or if we want to numerically, just under 1%. 10 times 10 to the minus 3 would be 10 times 10 to the minus 2, or 1%. I'm particularly tongue-tied tonight. I don't know why. Okay. So, now, next one. 13. In a box under your desk, you have 12 AA batteries. Unbeknownst to you, it's a wonderful word, 5 of them are dead. You grab 3 at random for your calculator. What is the probability that at least 1, okay, that's really crucial, at least 1 is bad. That's a real signal. Most of the time when you're looking at least 1 problems, or at least any small number, you're going to use complement. Okay, so the probability, I really didn't mean to do that. As I said, I'm just kind of clueless tonight. Okay, probability that at least 1 is bad is 1 minus the probability. I'm not used to using this keyboard. I'm going to come up with all sorts of excuses for making a bad video, but oh well. The probability that all of them are good, because those are the negations of each other. At least 1 being bad. It's not the case that at least 1 is bad. It means they've got to all be good. This is much easier to deal with, okay? Because in fact, it's exactly like the previous problem. It's 1 minus, okay. We're going to look at the denominator. Okay, let's see. Now, I realize that it's a complement problem, but now we're into the counting, and we got to ask our 2 fundamental counting questions. Order does not matter. Doesn't matter what order we pick these out. We just want to figure out if at least 1 is bad. And again, it's without replacement. You can't use the same battery 3 times for your calculator. That'd be kind of cool. It would save on money, but it's not going to happen. So again, we're going to get, well, let me just copy this in, actually. We're going to get something like this. Okay. We're actually still 3 on the bottom. We're still choosing 3 things. Okay, we've got 12 batteries to choose from. The whole sample space is how many ways can we choose 3 batteries out of 12? If we require that they all be good, then we actually only have 5 choose 3. Oh, sorry, 7 choose 3. There we go. 5 of them are bad, are dead batteries, so 7 of them are good. Almost made a big mistake there. So we look at the good batteries, there's 7 of them. When we figure out how many ways can we choose 7 of those, or 3 of those guys. Okay, and we're good to go. Let's just let it do the work. 37 over 44. Let me put that over here. It's going to look nicer. Okay. So we used complements, and then we went to our basic counting principles, and very much like problem 12. Okay. So notice that you're pretty much hosed here. It's really pretty likely that at least one is bad. You don't really want to pick them at random, and you want a battery tester is what you need. Okay. You're forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? Now, this one looks complicated, but it's actually set up in a particularly nice way. It doesn't, because it specifically says how many girls and how many boys, it's 2 completely different problems put together. You're just forming the girls part of the team, which is 10 choose 5. Oops. Let me just grab that. I just want to get a choose here. Okay. That's going to be 10 choose 5. That's the number of ways to choose the girls for the team. And then we got another choice, which is totally independent of the other choice. And we need to choose 7 out of 15. Order doesn't matter, and you certainly can't do it with replacement here, because you can't make a swim team of the same girl chosen 5 times, for example. So that's it. Our fundamental counting principle is if you're making 2 different choices that don't affect each other, totally independent, you just do them separately and multiply the answers. And then for each individual, the girls and the boys, you just got a standard choose problem. And and it's a lot of different ways. Let's put that up here just to make it pretty. Well, okay. So, a lunch counter has seats numbered 1 through 6. Why they number the seats, I'm not sure. 3 people come in and take seats at random. What's the probability that seats 1, 2, and 3 are occupied? Okay. Well, so it's basically taking just like cards numbered 1 through 6 and taking them out without replacement. And the order doesn't matter. And what's the probability that we get cards numbered 1, 2, and 3 for A? So let's see. We'll do A. Okay. So order doesn't matter. Even though you might think order matters because the seats are numbered, that's just to have 6 different objects, basically. We're not worried about what they don't say what's the probability that seat 1 gets sat in and then seat 3 and then seat 2. That would make order matter here. It's just which seats get chosen and which don't. Yes or no, not in order. And so it's just going to be very similar to what we had before. Make a little choose down here so I don't have to go up there. Okay. How many ways are there for people to sit down, period? Well, 3 people sitting out of 6 seats. 6 choose 3. And how many ways are there for the 3 people to sit in 3 particular seats? Well, it's 3 choose 3. In other words, there's no choice. If I say, hey, you 3, go sit in seats 1, 2, 3, and they say, wait, there's 6 seats, we want some choice. And you say, no, you got to sit in seats 1, 2, and 3. And then you don't pay attention to which people sit in which seats. Then you're just going to get 3 choose 3. Okay? So there we go. Now that's just 1. Let me just do that by hand. That's 1 over, and that's just 6 times 5 times 4 over 3 times 2 times 1. Just to show that I actually know how to do this by hand. I don't always just use the calculator. So the 6 and the 6 on the bottom cancel. So it's just 1 over 20. Okay. And then B. Okay. What's the probability that any 3 consecutive seats are occupied? Well, that's the kind of thing that could strike you as maybe a much more complicated problem. But let's just see how it's similar to A. A is a special case of what they're talking about in B. What's the probability that these 3 consecutive seats are occupied? We already found the probability of that. It's 1 out of 20. Well, what about if they asked what's the probability that seats 2, 3, and 4 are occupied? Well, that seems very similar to part A. Okay, so first, what is the probability that 2, 3, 4 are occupied? Well, there was nothing really special about 1, 2, and 3. It's just 3 particular seats out of the 6. So that's going to be 1/20th again. Okay. Well, what's the probability that 3, 4, 5 get occupied? That's 1/20th. And what's the probability that 4, 5, 6 get occupied? That's 1/20th. Because it doesn't matter which seats they are. There's nothing special about 1, 2, 3 versus 4, 5, 6. It's just the act of choosing 3 particular seats. This is the top 3 of all these guys here, out of the 6, and having 3 people sit in them. There's one particular way that they can do that out of the 20 different ways that they could have if you didn't tell them where to go. Okay, so let's see. We've got a bunch of different possibilities. 1/20th, 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 1/20th. Do they overlap? Well, if seats 1, 2, and 3 are the ones that are occupied, that's one situation. Could it be that 2, 3, and 4 are definitely occupied? No, there's only 3 people. They're either in 1, 2, 3, or 2, 3, 4, or there could be many other possibilities, but there's no overlap between the 1, 2, 3 situation and the 2, 3, 4 situation. So we've got 4 equally probable, mutually exclusive events. Aha, a great opportunity for using our rules of probability. Total probability is going to equal just the sum of these guys, 1/20th times 4. I'll just put 4 over 20, which is 1/5. So it's still not terribly likely that they'll actually be consecutive, but it's definitely more likely than a particular set of consecutive seats are occupied. So great stuff here. Mutually exclusive is the real thing. That mutually exclusive allows us to add up these 4 1/20ths to make 4 20ths. So watch out for that. Watch out for different cases that you get to add up because they're mutually exclusive. You might want to be careful to make sure they're really mutually exclusive, but it's a good example of that. I think B here, it seems like I think that would be a hard problem because people would take it in all kinds of complicated directions. But in this particular case, the logic, I didn't write this exam, but I think the logic is you've done A, B's pretty similar, concentrate on that similarity and try to leverage your result from part A. All right, hope that helps.